If you stand on the flight deck of an aircraft carrier and look towards the front, you will notice a massive structure on one side. This is the island. It houses the bridge, flight control, radars, and communication antennas. It is the nerve center of the ship. You will also notice something else. No matter if you are on a US Navy supercarrier like the Gerald R Ford class, a British Queen Elizabeth class, or a French Charles de Gaulle, that island is always on the right side of the deck. In naval terms, this is the starboard side. This layout is universal today. Every operational aircraft carrier in the world places its superstructure on the starboard side. This design choice is the result of human psychology, lessons from early naval aviation, and decades of carrier evolution. There's also a degree of path dependency. To understand why the island sits on the starboard side, we must look back to the origin of naval aviation in the early 20th century. The earliest aircraft carriers were experiments. Navies took commercial ships, cruisers, or battle cruisers and placed flat wooden decks on top of them. Designers quickly realized that a completely flat deck without any facilities created severe problems. A ship needs a bridge for navigating. It needs funnels to expel smoke from its boilers. If you put these structures in the middle of the deck, you block aircraft from landing. Early designers tried several solutions. The US Navy built its first carrier, the USS Langley, as a completely flush-deck ship. Its smoke funnels were placed on the side and could pivot downward during flight operations. The British Royal Navy tried a flush-deck design with the HMS Argus, routing boiler exhaust all the way to the stern beneath the flight deck. This made the ship incredibly hot and difficult to crew. Smoke also billowed out behind the ship, creating severe turbulence right where the pilots were trying to land. Navies needed a permanent structure to house command functions and elevate radars and lookouts. They also needed vertical funnels to direct hot gases away from the flight path. The solution was the island, a narrow building pushed to one edge of the deck. This left the rest of the surface clear for aircraft. The critical question was which side to choose. The decision to place the island on the starboard side was initially driven by the physics of early aircraft engines. During the interwar period and the Second World War, the vast majority of aircraft used rotary or radial piston engines driven by propellers. These engines featured a heavy mass of cylinders connected to a crankshaft that in turn rotates the propeller. Most aircraft have their propellers rotate clockwise when viewed from the cockpit. This rotation created a powerful torque effect. When a pilot applied sudden power to go around or to abort a landing, the clockwise rotation of the engine forced the aircraft to roll and swerve strongly to the left, especially at low speed. Pilots landing on early carriers had to cope with this constant leftward pull. If a landing went wrong, or if an aircraft suffered an engine failure on approach, the plane naturally veered toward the left. If the island was placed on the left side of the ship, which is the port side, these distressed aircraft would crash directly into the superstructure. And this is not good for the health of your ship and the pilot's likelihood of surviving the event. Planners realized that placing the island on the starboard side gave pilots an open, unobstructed safety zone on the port side. If a pilot lost control or needed to abort landing at the last second, the aircraft would drift away from the island rather than into it. This mechanical reality quickly integrated itself into human psychology. As generations of pilots trained on generations of aircraft carriers, turning left became a deeply ingrained instinct during emergencies. When a pilot performs escape maneuvers, their brain relies on the survival habit. For a carrier pilot, that habit was to clear the deck by breaking left. Even as aircraft transitioned to jet engines, which do not suffer from the same torque effect as early rotary engines, the psychological default remained. Pilots were conditioned to look left and to brake left during botched landings. Moving the island to the port side would require rewriting every basic instinct taught to naval aviators from the very first day in a flight simulator. Despite this emerging consensus, one nation decided to challenge the starboard island layout. In the 1930s, the Imperial Japanese Navy experimented with an alternating fleet concept. They believed that two carriers operating side by side should form a single tactical unit. To make flight operations more efficient, Japanese designers reasoned that the carriers should have mirrored flight paths. This means for some carriers, the island should be on the left or the port side in naval terms. The Imperial Japanese Navy modified the carrier Akagi with an unusual port island, while her sister ship Kaga received the usual starboard island. Later, they custom-built the carrier Hiryu with a port island to operate alongside the Soryu, which had a starboard island. The idea made sense on paper. The two ships could steam parallel to each other. Aircraft from Soryu would recover by turning left, while aircraft from Hiryu would recover by turning right. This would prevent the traffic patterns of the two air wings from overlapping in the sky, reducing the risk of mid-air collisions when they land. In practice, the experiment was a disaster. The port island on the Hiryu and the Akagi created severe aerodynamic problems. The wind blowing over the deck, known as wind over deck, is critical for carrier operations. A carrier must steam directly into the wind to generate enough lift for aircraft to take off and to enable safe landing. As air moves over the ship, the island acts as a massive obstacle. It creates a wake of turbulent air downwind of the structure, which settled directly over the final approach path of the aircraft. Pilots flying into Hiryu encountered violent downdraft and crosswinds at the exact moments they needed stability. Because of the clockwise rotation of the propellers on early Japanese aircraft, carrier fighters naturally drifted to the left when taking off or landing. Having the island on the left meant pilots were flying dangerously close to the structure. Japanese pilots, like their Western counterparts, were generally conditioned to pull left when a landing failed. On the Akagi and Hiryu, pulling left meant crashing straight into the island. This created an additional layer of stress for pilots based on these carriers. The operational confusion inside the ships was also severe. Internal layouts had to be inverted from elder Japanese carriers, which disrupted the standard movements of munitions and aircraft on the hangar deck below. By the time the Second World War began, the Imperial Japanese Navy realized the mistake. The port island configuration offered no real tactical advantage and significantly increased the risk of incidents. When Japan designed its subsequent carrier classes, such as the Shokaku class and the Taiho class, they returned exclusively to the starboard island layout. The losses of Akagi and Hiryu at the Battle of Midway in 1942 marked the literal end of the portside island experiment. No navy ever again built a port island carrier. Regardless of the site chosen for the island, naval architects have long understood that a carrier must have its superstructure restricted to one side only. You cannot place islands on both sides of a flight deck. Doing so is dangerous. When wind blows between the two structures, the air compresses and accelerates dramatically. Geo islands on opposite sides would create a wind tunnel right over the flight deck, making landings very difficult due to severe and volatile winds. Restricting the superstructure to a single side ensures that the air can flow cleanly across at least one half of the deck. The final element solidifying the starboard island is path dependency. Once the major carrier navies settled on this arrangement, every new generation of carriers inherited decades of ingrained lessons. Knowledge sharing across different international navies further standardized the layout of flight decks. Designing an aircraft carrier is an incredibly complex engineering challenge. It requires managing the movement of fuel, ammunition, crew, and aircraft within a constrained footprint. When a design already works, architects do not change it without a compelling reason. The entire global ecosystem of carrier aviation is built around the starboard island. Consider the physical layout of modern flight decks. Since the 1950s, carriers have come with an angled flight deck. This innovation, pioneered by Britain and perfected by the US Navy, allows for simultaneous launches and recoveries of aircraft. The angled deck always juts out to the port side of the vessel. This design aligns perfectly with a starboard island. The landing strip points away from the island at an angle, usually around 8 to 10 degrees. This creates a clear safety zone on the port side for aircraft that miss the arresting wires. If a pilot misses the wires, they apply full power and fly straight ahead, safely clear of the island on the starboard side. If you were to move the island to the port side, you would have to mirror the entire ship. The angled deck would have to jut out to the starboard side. This would disrupt every standard international operating procedure. Aircraft carriers from different navies frequently operate together. Pilots from the US Navy can land on French carriers like the Charles de Gaulle during joint exercises. This interoperability is possible because the deck layout and operational procedures are similar at a basic level. A pilot expects to see the island on the right and open spaces on the left. Changing this layout would break global expectations. Breaking interoperability between nations and require an expensive re-engineering of the flight deck, optical landing systems, and pilot training. Even the UK's Queen Elizabeth class, which features an unusual two-island design, maintains this rule. The ship has two smaller islands instead of one large superstructure. The forward island houses the ship's bridge, while the aft island houses flight control. This separation reduces electronic interference between radars and optimizes internal gas turbine exhaust routing. Crucially, however, both of these islands are placed on the starboard side of the ship. The port side remains completely open, preserving the traditional safety margins. Ultimately, the placement of the aircraft carrier island on the right side is a classic example of historical reasons locked in by human psychology and path dependency. What began as a practical solution to counter the torque of clockwise rotating propellers became an international standard. It was validated by the failed experiments of the Imperial Japanese Navy. It was then codified into the global system of naval aviation through the development of the angled flight deck. Today, the starboard island is a fundamental architecture that ensures safety, certainty, and efficiency in the most dangerous operating environments for combat aircraft. As long as manned aircraft fly from ships with flush decks, the island will remain firmly anchored to the right. If you enjoyed this video, you should also enjoy my video covering the insane engineering of the nuclear supercarrier, the Nimitz class, on your screen right now.